Hi everybody, so this is going to be the last video on our chemical equilibrium theory side for bite-sized chemistry. So just a reminder here that you need to know those definitions. They've been asked every year, and there's a few of them there as well. And secondly, the stresses, pressure, temperature and concentration all need to be known. Pay particular attention to temperature because that's the one that can catch students. And then there's the manufacture of ammonia and H2SO4. So last time we finished on, I think it was like 2011. So that means we're moving on to 2010. This is the year I actually did my leaving cert. So 2010, phosphorus 5-chloride decomposes into phosphorus 3-chloride and chlorine at temperature at a 500 Kelvin. According to the equation here, you're asked for the definitions here. This is a reversible reaction, dynamic equilibrium, explained under the terms. Why is equilibrium described as dynamic? Okay. Reversal reaction just basically means that the products react to reform the reactants. That's all. The products react to reform their reactants. It's a chemical equilibrium, we stated that already, that the forward reaction equals the reverse reaction at an equal rate. And it's dynamic because the reaction doesn't stop. It's continuously forming the products and reforming the reactants. Okay? Now, when the temperature of the equilibrium of the mixture is increased, the phosphorus 5-chloride decomposes further. Okay, so when we increase the temperature, this guy over here decreases more. It goes towards the product side over here. Is the reaction endothermic or exothermic? And justify your answer. So let's repeat that again. When we increase the temperature, it drives the reaction towards the product side. So therefore, it must be endothermic. Okay, oh, I have that written down wrong here. I knew I did. It's endothermic because higher temperatures favor the product side. It's the exact opposite. Okay, and they're just something you have to learn off. In the past, we've been dealing with what happens if you cool things down. In this case here, now we're asked what happens if you increase the temperature. Okay, so if we increase the temperature and it drives the reaction towards the product side, it's endothermic, and you state your reason why. Higher temperatures drive the reaction towards the product side. Now, E. What change, if any, would you have on the increase in pressure will have on the effect of Kc, and to explain? Well, we've seen this one several times now at this stage. Pressure has no effect on the Kc. The value of the Kc is constant at constant temperature. In other words, temperature is the only thing that affects the Kc. Okay? 2008, everybody. So, we're going to skip all that for a moment, and we're just going to go down to here for A. What is meant by chemical equilibrium? Forward reaction equals the reverse reaction at equal rates. The colour becomes pink. Has the reaction ceased? And to explain, well, we can see here we're going from a purple to a colourless, so an in between there would be pink. The reaction is at an equilibrium, and no, it has not ceased because equilibrium is in a dynamic state, which is what these arrows mean here. Okay. State Le Chatelier's principle, we've done that loads of times now. Use Le Chatelier's principle to predict the effect of a decrease in temperature. Okay, so if I decrease the temperature, what happens to the yield of iodide over here? Okay, first off, we can see here that the reaction is not, there's no negative there, so it's endothermic. An endothermic reaction. Okay, overall. So if I decrease the temperature, okay, it would lower the HI yield. Okay, it's the exact opposite to exothermic. If that was exothermic, guys, and I decrease the temperature, it would increase the product over here. But it's not. It's the exact opposite. So because it's endothermic or overall, if I decrease the temperature, okay, the yield of hydrogen iodide decreases. Now, what happens to the intensity of the colour on the equilibrium mixture? So again, if I decrease the temperature here, what happens to the intensity of colour? Well, we've already just said it there. The intensity, if it's not forming the product, then and therefore has to be going towards the reactant side, the intensity would increase because it's a darker side over the side on the reactant side. So it would increase, like go darker, more purple. Okay, So just to bear that one in mind. And what change, if any, will an increase in pressure have on the yield? And to explain, well, let's look at it. They're gases anyhow, so it will have an effect. But there's the same number of molecules either side. There's 2 on this side and there's 2 on this side. So therefore, pressure has no change on the yield because the same number of molecules either side of the equation. Next, I think it's our final one, thank God. 2006, the Chatellier's principle again. So look, I'm like a broken record at this stage. You should have an idea of it by now. If not, sure, God help you. Let's move on to part I though. When the solution has become blue, has the reaction ceased? And to explain, yeah, the reaction never ceases for equilibriums, guys. Okay, it's dynamic. Part 2. The forward reaction, and that doesn't matter what color it is. It could be a mixture of blue and pink. It could be totally pink. It could be totally blue. It doesn't matter. There will be some sort of equilibrium there if those arrows are there. And if there is an equilibrium there, it will be dynamic. So for part 2, the forward reaction is endothermic. State and explain the color change observed on cooling the reaction mixture. So if it's endothermic, I'm just going to write over here that delta H equals, and just make up a number, it doesn't matter. We'll say 28. Okay, kilojoules per mole. Just as a guide, okay. Endothermic, it's going to be positive here. Okay, so forward reactions endothermic. State explain the color change on cooling it. So if I cool it, it's actually going to drive the reaction towards the left-hand side, the reactant side. So therefore, it should be going at pink. If the reaction is endothermic, a decrease in temperature shifts the reaction towards the left-hand side, which is over here. Part 3. Other than heating, mention one way of reversing the change caused by cooling the reaction. Now, this is a tough one. Some people will be thinking, oh, can we go down the route of pressure? Now, I'd recommend you don't go down the route of pressure, simply because if we're looking at it, we're adding hydrochloric acid. Okay, we can assume that this is in a liquid format because we're dissolving things in water, and pressure has no impact on liquids or solids for that matter. It's definitely not gases that we're dealing with here, so ignore pressure. So how could I reverse the change here? So I wanted to go to a blue colour. It was a pink. I now wanted to go to a blue colour. Well, think of your concentrations. Just dump in a load more HCl. And if I add in some HCl, some chlorine anions, it'll drive the reaction towards the product side. So adding some HCl drives the reaction towards the product side. Now, I should bear in mind there, or should tell you, it doesn't have to be HCl that we're dealing with here. I only said HCl because I have it over here. You could, in theory, add in anything else that gives you chlorine anions there, okay? But HCl was the easiest because it's obviously as mentioned over here. So guys, look, that brings it towards the end of the videos. We've gone through quite a number of years there for the theory. And again, it boils down to the definitions. There's a few of them there. There's Chatellier's, chemical equilibrium, dynamic state, reversible reaction. Then we have the stresses, pressure, temperature, and concentration. And pressure and concentration are generally okay. Okay, temperature is the one that catches students. And if you overthink it, it can be problematic. So sometimes it's just best to try and learn off the definitions, the rules, and then not to overthink it as best as possible. And then you've got the manufacturer, H2SO4 and H3. And that usually comes under the umbrella of why do we not use low temperatures, or why do we not use high pressures, and then trying to find I suppose a balance, an equilibrium as such. Okay guys, look, I hope that helped with your studies in chemical equilibrium. I'll be doing a maths version of this fairly soon, but the maths is all there for the most part. If you look at the maths of chemistry on the Conical Flask, or you look at the videos that I've put up on it in the lesson of chemical equilibrium. Okay everybody, best of luck with it.